Good morning, everybody. Welcome to this second part of the third lecture. And today we will continue with measurement of power. We will see how we, in practice, measure the power. And then we will move to the measurement of the RMS value. And if I have time, I will give you some introduction about the operational amplifier, which is a circuit we will use very, very often in this course because it's very useful for many applications in the field of measurement. Now, before starting this lecture, somebody yesterday asked me after the lecture about the grading system, because of course, that's the most important thing. So typically, we give 100 points total, which corresponds to the grade A. And out of these 100 points, we give 60 points for the final exam. So you will take a test at the end of the course where you can get 60% of the total points. Oh, somebody needs the link. Oh, I can maybe give you this, which is this is the whole list of the, okay. So let me check. Maybe I should make some permanent link to the lecture so that you can retrieve it whenever you want. Okay. Anyhow, maybe saved on your bookmarks this link. Okay. Fine. So let's continue. We will give 60 points for the final exam. What is in the final exam? There will be some calculations about uncertainty. Typically, you will need maybe to design a little measurement system. You will have some theoretical questions where you have to answer, I don't know, what is this type of sensor? How do you measure this? Why do you use this solution, not the other solution? Just a little remark. Some students complain because they believe they want some model for all the problems to solve. That's not how an engineer work. Because the point is that as a matter of fact, you will not have model of problems to solve in real life. In real life, you get knowledge, maybe a little bit of knowledge from courses you study at the university. Most likely, more knowledge you will get studying all your life. And you will try a solution, a method to solve a problem based on the knowledge you have. Most of the times, you will find some problems. You don't know how to solve it, and there is nobody telling you which method, which problem to use, which pattern of equations to apply. So I will not give you a list of problems and you will hope that you will find one of them. Otherwise, it's just memorizing some steps, and that's something a machine can do. Okay? So in your case, you have to learn the concepts, and when you have all the knowledge that you will learn during this course, you will be able to solve these problems, okay? So don't expect me to give you a list of patterns of problems to solve, and expect to find in the final exam one of them. Let's be clear about that. So your task now is to study and understand deeply the concept I'm trying to teach you here now. There will be 2 tests for 20 points. There will be intermediate test, multiple choice. In this case, they will be done on Moodle. There is an application on Moodle which allows you to make some tests. So in the middle of the semester, I will organize 2 tests about what we studied during the previous weeks. So be sure that you can access to your Moodle, and I will tell you how you can access to the test. We will make most likely one mock-up test just to check that the system works. You can answer so that you will be confident with the system when we make the real test, okay? And then there will be 20 points for the laboratories. Yesterday I uploaded a new video for the second laboratory. It's about measurement of small voltages amplified with operation amplifier. You will see this topic in the next lecture. Meanwhile, just see this video, and as usual, there will be a question at the end of the video you will have to answer. For that, I will give points, all these activities, and then there will be the extra point that you can gain. For instance, yesterday I made a question. I still have to upload this on the MS Teams, the assignment. It's not mandatory. It gives some extra point. In that case, 5 extra points, which is quite a lot. It's like 1/4 of the points you can get from the intermediate test. And the labs. So all these extra questions I put there on MS Teams just give you extra points. So 5 points for that question is like 1/4 of the labs. It's quite a lot. It's half a grade. So don't miss the opportunity to gain these points. Okay? This was for the grading. As I told you, I have uploaded already the next laboratory on MS Teams, and now we can start with the lecture. If there is any question, as usual, drop it in the MS Teams comment section. Okay? Fine. So yesterday we saw how to measure power, active power, reactive power, and all that sort of jazz. We also saw one type of multiplier, which is the digital multiplier. Simply, we acquire, we digitize both voltage and current, we multiply them, and then we get the power. Of course, it's not so simple as it looks like, because you cannot simply multiply the samples that you get from digitizing the current and the voltage, because otherwise you don't have samples enough. So you have to do something else, and that was your task, to find out what you should do with those samples of current and voltage. Of course, the alternative is to sample at higher speed, and then you can simply multiply, and Bob's your uncle. Now, today we will study more in details analog multiplier. Again, you have to multiply current and voltage, and you can do it also without sampling these two signals, but multiplying them in the analog world. There are different techniques. The first one is is based on Hall effect. I'm not sure if you ever heard about Hall effect. That's a very old physical effect, which was discovered long time ago, and is based on the fact that if you have an electric charge moving in a magnetic field, so for instance, you have a current here, which moves in a magnetic field, you have your magnetic field, and you have a force which applies, the current experiences some force. That's a basic principle which is behind electric machines, for instance. And this effect can be used to measure magnetic field. As a matter of fact, Hall effect sensor is used to, most of the times, to measure magnetic field. So you have a chip. Let me find, where is the eraser? Here. You have a chip of semiconductive material. You inject a current. The current flows inside this chip of semiconductive material. Since you apply a magnetic field, you will have a charge, and the charge will experience a magnetic force. Therefore, will move. Then, it means that you will have more charges here than here, or vice versa if you change the polarity of the sign, if it's negative or positive charge. Then from one side, you have more negative charges than from the other side. And this means that between this point and this point, you can measure a voltage, okay? This voltage will be proportional to the disequilibrium of charges, which is given by the force. And the force is proportional to the current, and it's proportional to the magnetic field. Therefore, at the end of the day, you have a voltage which is proportional to the product of the current and the magnetic field, right? So the larger is the current, the larger will be the voltage, because you have more charges which are more disequilibrium of charges, more negative or positive charges from one side and the other side. But also, if you increase the magnetic field, you have a larger force. The larger is the magnetic field, the larger is the force. So therefore, you will have a larger disequilibrium of charges. As I told you, this is very often used to measure magnetic field. You inject a known current, a constant current, and then you measure the voltage, which is proportional to the magnetic field. For the record, it's not the best magnetic sensor at all, but it's very cheap. That's the reason why, for basic applications, it's very commonly used. This is probably one of the most commonly used magnetic sensor in the world. In this case, we use it to multiply two signals. How? Well, we have to multiply voltage and the current in order to compute the power, right? So, one signal will be used, so the current will be used to generate the current in the Hall effect sensor. Okay? So this is the current. It will not necessarily be the same current. You might change it simply because the current that you inject in the Hall effect sensor is not, it must be smaller than the current that you want to measure, right? Then the voltage will be used to create a magnetic field, or in this case I'm saying B, so it's magnetic flux density, okay? But we say magnetic field even if correctly, more correctly it should be magnetic flux density, okay? For instance, I apply a voltage to a coil. The coil will have, therefore, a current, and the current will generate a magnetic field. So, for instance, here, above this, let me draw it again. Let's say that you have a chip like this from the side. You inject a current here. Then here, you have a coil. You apply your voltage. And therefore, you will have a current which creates a magnetic field, okay? So, also in this case, you will need maybe, most probably, to change the voltage that you want to measure into another value of voltage that you apply to the coil, because it will require another value of voltage. And therefore, you have here a force which will be proportional to the current that you derive from the current that you want to measure, and the voltage which you want to measure, okay? I will tell you some more details about Hall effect sensors when we will study magnetic sensors in the second part of this course, okay? Another system that you can use is the Log Antilog Multiplier. Probably you remember from your lectures of mathematics this very funny property of the logarithm. If you have the logarithm of a product, so logarithm A times B, is equal to the sum of the logarithm of A plus the logarithm of B, okay? And how can we use this property of the logarithm to compute two signals? Well, that's very simple. Instead of multiplying two signals, A and B, we sum their logarithm. This is because summing two signals from the analog point of view is very simple. You can do it with an operation amplifier in a summing configuration. It's extremely simple. So what we do is to transform A and B here into logarithm of A and B. Then you sum up the logarithm of A plus the logarithm of B. You get the sum of logarithm A plus logarithm B, but this is equivalent to the logarithm of A times B. And therefore, you can, at the end, go back and compute the anti-logarithm, which is just a fancy name for exponential, and get A times B, okay? So we move from A and B to their logarithm. We sum, we don't multiply, we sum. But the sum of the logarithms is equal to the logarithm of the product. So when we compute the anti-logarithm, we get the product, okay? Now, how would you do, from the practical point of view, the logarithm and the anti-logarithm? Let's see if anybody of you in the comment section can guess what's the physical principle that you can use to compute the logarithm and the anti-logarithm. Let's see if you have any idea. And of course, don't go on Google and search logarithm amplifier, anti-logarithm. Try to guess by yourself if you have any idea of how to compute the logarithm, because summing is something that we can do very easily. Now let's see if you know. You don't need specifically the circuit. It's just enough to tell me if you know any element, any device which can give you a relationship of logarithm, anti-logarithm, between the input and the output of this device. Let's see if anybody has an idea. What you can use? Not a resistor, for instance. If you have a resistor, you have a current which is proportional to the voltage you apply to the resistor, right? So resistor, no. What else? What else has a relationship which could give you the logarithmic behavior? Now, I'm trying to talk and talk and talk to fill the time until in the comment section somebody will answer. No idea? A diode. Okay? You probably know that if you have a diode and you apply a voltage D, you will have a current ID. And then let me erase this part here. Oops. So you apply a voltage VD, or maybe I will draw it as I did in the schematic. And then you get the current. And you get an exponential, right? So you have a current in the diode, which is roughly the saturation current times the exponent of the voltage, the diode, ideality factor, the thermal voltage. Thermal voltage is just a value which depends on the temperature. This effect is useful if you want to measure the temperature. A diode is a rough sensor of temperature because the current depends also on the thermal voltage, and therefore, which depends on the temperature, okay? So there are some methods to to use a diode as a sensor of temperature, if you want. We will see in the second part of the course when we study the sensors of temperature, okay? Now, the current is proportional to the exponent of, to an exponential of the voltage that you apply. Therefore, the voltage is proportional to the logarithm of the current, okay? So this is the current of the diode. So log antilog is done using a diode in some special configuration, typically in the input or feedback position of an inverting amplifier, okay? Fine. Then there is a time division multiplier. The basic principle, there are several circuits how to in practice make this time division multiplier. The principle is that you create a square wave, or there are also some circuits with triangular wave, where you change the duty cycle with one signal, and then you change with the amplitude with the other signal. So at the end of the day, the average value depends both on the amplitude, one signal, and on the duty cycle, okay? So you have to transform a voltage into a pulsing square wave with the duty cycle. Duty cycle means how much, oops, I have to change the chalk. The duty cycle is T1 divided T1 plus T2, okay? So it tells you how often the signal is on over the total time of the period of the square wave, okay? And then, therefore, at the end, the average value of this waveform is depending on both the two signals, V1 and V2, used to create this square wave. We have already studied the electronic Voltmeter. As I explained yesterday, you have to sample and then not multiply, but do something else to the digital signals of the voltage and the current. Somebody asked me, okay, what is this box here where you have both I and V? As I explained yesterday, you have to convert current into the voltage, okay? Maybe I can leave here. So, you have different means to transform a current into a voltage. We can have a shunt. A shunt simply is a resistor here. You inject the current in your circuit and you measure the voltage here, okay? One of the problems is that you don't have galvanic insulation, okay? So you don't have anything which decouples, which separates your circuit of measurement from the circuit where you have sometimes large current, okay? So this might be dangerous. You can use all FX sensors. As we saw before, you can measure the magnetic field using these cheap sensors, and therefore what you do is to take the current, inject it in a cable or in a bus bar if the current is very large, and so you inject the current, and then this will generate a magnetic field, and you can put your magnetic sensor here, which measures the magnetic field created by the current, okay? I've already mentioned probably that this problem is not so simple as it looks like, because as the frequency changes, there is a different distribution of the current, especially in this kind of geometry, okay? where you don't have symmetry given by the cylindric shape. And therefore, you have to be very careful where you put your sensors. There are several methods how to compute. There is a lot of science behind that. Okay, it's not so simple. It's not just that you put a sensor there. Of course, if you have only one frequency, it's obvious. You don't have this kind of problems. But especially now with a lot of higher frequency in the network, you need to be able to measure the current also at higher frequencies. Okay. A very important topic is about the transformer. Many times you need to reduce these values of current and voltage that you want to measure if they are too large. So what do you use? Use for current, if you want to decrease the value of the current, a current transformer. Now, I'm not really sure if you know what is a transformer, so please, I should have done the survey before, like I did with the operational amplifier. So please drop me in the comment section if you know what a transformer is. Meanwhile, I clean the grain board. Please, please, please answer to my question. Because if you don't know, I will just explain very quickly, okay? So, tell me if you know what a transformer is. This is also a test. I can check if you are really live there or if you are just presenting. Okay, somebody knows what is a transformer? Somebody else? Yes, I think, oh, wonderful. So, you probably know what is a transformer. Everybody knows. Perfect. Just for quickly, okay, somebody doesn't know, so it's enough that one doesn't know. I will explain. Transformer is based on a ferromagnetic core. Ferromagnetic core can be made by, okay, I have two students who do not know what is a transformer. Perfect. So, you have a ferromagnetic core. Now, you have a primary winding, so the first coil, where you apply a current, you apply voltage, and then you get a current. This will create a magnetic flux. This is time varying, okay? Okay, so you have the voltage V1, which is a function of time. It works only if the voltage changes in time, okay? Then you will have another coil where you will obtain a voltage with the same frequency, which is the effect of this flux generated by the first coil, which arrives here, and since the flux changes in time, you will have a voltage induced by the time variation of the flux, okay? You know that if you have a flux in a coil, you have a voltage, you have a magnetic flux. The voltage will be, if this is the number of the turns, proportional to the number of the turns times the derivative of the flux in time, okay? So, if you create a constant flux, it will not generate anything at the output, but if you have a time-varying flux generated by a time-varying voltage applied on the first coil, then it will generate a voltage output. Now, if you have a different number of turns, you will have a different voltage, right? So if you have here 10 turns and here 100 turns, here at the output you will get 1/10 of the voltage that you apply here, okay? Why do we have this ferromagnetic core? Because we need the core to bring the flux from the first coil to the second coil. The ferromagnetic core is like the highway for the magnetic flux. If you create some magnetic field, the resulting flux will be flowing in the core and not in the air, or at most of the flux will flow in the core, because the magnetic field likes the ferromagnetic core. For the magnetic flux, the air is bad. Ferromagnetic core is good. So it feels comfortable to stay inside here, the ferromagnetic core. So instead of going anywhere else, it will stay inside the ferromagnetic core, and that's the way you can use to bring it here from the first coil to the second coil, okay? Fine. So the only reason why we have a ferromagnetic core is that we can use it to lead the flux where we want, which means to the second coil. So in this configuration, you can use the transformer to reduce, for instance, 10 times the voltage. If the ratio is 1 to 1,000, you reduce it by 1,000 times, and so on. So different number of turns, different ratio. If you decrease the voltage, then you increase the current, because the power ideally should be the same, okay? So if I have here the current I1, and here I have a load, therefore I get a current I2, the power in the input, P1, which is the, let me erase, because probably you cannot see very well. So V1 times I1 will be necessarily equal to P2, which is V2 times I2, okay? Of course, this is not real, because otherwise we would have a perfect machine. There are some losses, but generally speaking, in an ideal case, we will have the same power which enters here, voltage times current, which is equal to the power at the output, voltage times current. Now, if you reduce 10 times the voltage, you increase 10 times the current, okay? The power is always the same, so if you have voltage and current and you decrease the voltage, to have the same power, you need to increase the current, okay? In this configuration, therefore, you decrease the voltage and you increase the current. If you flip it and you have 10 turns here and 1,000 turns here, it does the opposite. So it does decrease the current and increase the voltage, okay? Fine. So in this configuration, for instance, we have 1 to n configuration, and 1 to n ratio of the turns of the transformer. So therefore, we reduce the current by a factor of n. Now, at the output, therefore, you have this transformer. You have this transformer. You inject the current. Here you have all your system. Then you reduce it by a factor of n. And then here you put an ammeter, okay? Whatever type of ammeter. Could be, for instance, instead of having an ammeter like that, you could have, as I said, a resistor, and then you measure the voltage, right? So the current here divided by n times will flow mainly in the resistor, because the voltmeter has very large input impedance, if you remember. And therefore, we measure the voltage on the resistor, okay? This is one example. Generally speaking, I have here an ammeter. And you remember what we said about the ammeter? We said that the ammeter is equivalent to a short circuit. So that resistor, for instance, that we used before, must be a very small resistor, okay? So this means that here the secondary coil of the transformer will be short-circuited, okay? And this is very important because a basic rule that you must always remember when you work with current transformers is that the secondary coil must be short-circuited at all times. Why? Because guess what happens if you open this circuit? Please try to guess what happens if, by accident, you're there in your factory and you're measuring this current and say, oh, then I need that current, I need this ammeter. But you know, it's installed there after a current transformer. Oh, who cares? I will take it and I will return it back later. Nobody will notice I took it, right? So what happens if you go there and poof, you take out your ammeter? What do you think it will happen? Well, of course, your boss, if he realize that you stole the ammeter to do something else without telling him that you took the ammeter, maybe will get a little bit angry. But that's not what I was referring to. What happens if you remove an ammeter? And of course, if you are measuring something, if everything is off, nobody cares. Let's say that you decreased the current a lot, which means that you increase the voltage, okay? So one of the problems which will happen is that the current wants still to circulate to fulfill this equation. So here you have a current, and here the secondary, you will generate a current. And the transformer wants to generate the current. So once you open the circuit, once you remove the ammeter, you have a current which still wants to circulate. So it will try to go on the other side, creating a spark. You could have a spark, and this could be dangerous under some condition. It could be dangerous because if it's a very large spark, it can catch your eyes and burn your eyes like 2 egg balls. And then, in other cases, the spark might ignite in some fire if the factory is full of explosive gases, for instance. So it's extremely dangerous. That's why, on current transformers, you always find, let me do it better, you always find a switch over the ammeter terminals. Why? Because they tell you, sometimes they even write it, like before removing the ammeter, always close the switch. Because in this way, you can close the switch, have a current flowing here, and always keep the short circuit running. Always have the current running in the short circuit, and then you can remove the ammeter, okay? So you always need a short circuit, and that's why they typically they typically make you a switch to let you close the short circuit before removing the ammeter. Otherwise, most of the times you would forget about that. But if you see the switch, maybe, even if it's not written there that you should close it, if you are about to remove the ammeter and you see the switch, say, oh, why is there a switch in this position? Maybe I should close it, okay? Fine, so always remember to close the secondary coil before removing the ammeter. And here is the explanation, okay? About the voltage transformer, that's the opposite. So instead of removing, by the way, there is an important thing. In the laboratory, it's quite interesting because most of the students get confused in this case, okay? So, typical configuration of the current transformer is a toroid, something like that, where you inject the current here. The current flows through a wire which enters in the toroid, and then you have a lot of turns which become the secondary coil, okay? Then, in some cases, I don't know, you can put a resistor and measure the voltage here, okay? Fine. So if you have 1,000 turns on the coil, on the secondary coil of the current transformer, you reduce the current by 1,000 times. Fine. The question that often makes my student confused is, where's the first coil? I have only a wire which enters in the toroid. So where is the turn? There is no turn. There is only one wire which enters in the toroid. At least I would like to see, if this is the toroid, one turn like this. But here I have just a wire which enters in the toroid. So where is the first turn? There is not even one turn, right? No, there is a turn, and even if you don't see it. If this is the load, and here there is a generator, do you see now the turn? This is the turn, okay? The whole circuit, sooner or later, it will close. So here you have a whole turn, which is very large here, which takes this portion of the toroid, okay? So this is one turn. So if you take your toroid and you make something like this, you don't have one turn, but you have two turns, okay? This is the turn. Even if you don't see it, typically you see only this portion. So you see only one wire which enters in a toroid. And you think, okay, where is the turn? Well, watch where the wire goes. Goes to the load, goes back to the generator, and returns here. Eventually it must close, because if it doesn't close, there is no current. So if there is a current, the circuit will close somewhere, and if it closes, it means there is a ring, which is a turn which includes a portion of the toroid inside, okay? So always be careful about that. No, I tell you this thing because I saw on YouTube some wannabe scientist who claimed that in his circuit there was no induction, there was no an inductor. So the physical principle he discovered was not possible to be explained by physics, because it required the circuit to have some inductive behavior, and there was no inductor there in the circuit. That guy didn't realize there was an inductor. He simply didn't see it because he was missing this basic concept. So once he considered that inductor, of course, all the physics was holding there, okay? For the voltage, that's the same thing, but you flip everything over. So you take the voltage the transformer, you flip the ratio, and you reduce the voltage by the factor of the ratio of the turns, okay? Now, very important thing, again, just a trivia for the weekend. Let me clean here. So far, everything okay? Don't forget, you can make me questions, even if I don't call for them, okay? The ferromagnetic core is not ideal, okay? Any ferromagnetic material is based on a BH curve, which eventually goes into saturation. Now, forgive my poor drawing skills, okay? Now, it could have a large coercivity in this, like in this case, or a very slim coercivity, okay? Like in this case. But always it will arrive into saturation. What does it mean? It means that H is the magnetic field that you create with the first coil. You inject some current, the current creates a magnetic field proportional to the current, okay? So you apply a current and you create a variation, time variation of H. This corresponds to a time variation of B, okay? You change your magnetic field, you create with the current a magnetic field H, it does change in time, and as a result, you get a magnetic flux density B, which is changing also in time. Then you integrate B over the area, you get the flux, and the derivative of the flux is the voltage, okay? So, if you have B times the surface, you get the flux, and you get the derivative, the voltage is proportional to the derivative of flux in time, okay? Now, what happens if you add a DC field to the field that you create with a coil, okay? Let's assume that you have the same ferromagnetic material, okay? Same ferromagnetic material. You have the same variation of magnetic field, okay? So you have the same delta H, but it's shifted. It's not around zero. It is shifted by a DC field, okay? Now, let's see what type of variation of B it will produce. Well, almost nothing, okay? you still have the same variation of magnetic field H, but now this variation occurs into the region of the ferromagnetic material, which is in saturation. So for the same variation of magnetic field H, you get almost nothing in variation of magnetic flux density. And this means that, therefore, the variation of the flux is 0, and therefore, the voltage, which is proportional to the derivative of the flux, will be 0, okay? Be careful. The output voltage is based on the induction law. It means that the flux might be large, but if it doesn't change in time, it doesn't create any output, right? So, once you are in saturation, the magnetic flux density, and therefore the flux, will be large, but they do not change in time. Therefore, they will not create an output voltage. And I'm not sure if you understand now where I want to arrive with this point. Well, what if you have an energy meter? A meter which wants to measure the power that you absorb, and therefore, integrating that power at the end of the month, tell you how much energy you absorbed and how much energy you have to pay. Well, what if there is a method, what if there was a method to add a DC field? You could still continue to absorb a current. The current in the current transformer would still change, create a time variation of magnetic field, but then you get nothing at the output, like if there was no change of magnetic field. And that's what somebody tries to do. They will add a DC field to the current transformer using a permanent magnet, a very strong permanent magnet. With this permanent magnet, they bring the core into saturation, and therefore they don't pay energy because it seems there is no signal at the output of the transformer. Okay? Disclaimer, this is illegal, so don't do it. I'm not teaching you these things because I want to teach you how to steal electrical energy. First of all, you are tampering a measuring device. So you are doing something against the measurement word, and they cry, so don't do it. The second thing, it's illegal. So if they find you doing something like that, you will face criminal consequences. So don't do it. I'm just teaching you these things because maybe you will be on the other side of the law, so you will be the one trying to catch these people, okay? And punish them for the stealing of electrical energy. Of course, those who design these electric meters are not idiots. They know that people want to try this method. So they, of course, try different methods to avoid this problem. They design cores which have, for instance, saturation at a much larger field. So you will need a very, very large DC field in order to bring the core into saturation. They will, for instance, put the current transformer in a place far away from the case of the instrument. So you are far from any point you could put the magnet, and the further you are, the lower is the magnetic field you can create. Okay? Very often they can put some magnetic sensor there. As a matter of fact, such a large field is very easy to be detected by even a cheap magnetic sensor which costs a few crowns. So just put a magnetic sensor, and if they detect some very large magnetic field, it could ring a bell and send a signal to the company that somebody is trying to cheat on the electrical energy measurement, okay? This typically happens for meters of industries. For like our meters that we have at home, typically they use a shunt resistor. But for industries where you have very, very large current, typically they need to use some current transformer to measure the current, and therefore you have this kind of problem, okay? Fine. Let's continue. So if you want to measure the power with measurement transformers, you need to use, for instance, both of them. You need to use one for the current, and then you connect the wattmeter at the output, the current side of the wattmeter at the output of the current transformer, and the same for the voltage, okay? Fine. Here, so I arrived to this conclusion before. What if you want to measure the energy? Well, as a matter of fact, we have already solved the problem, because you need to measure the power and then integrate it in time. So what you do is to use the voltage, the signal that you obtain from the measurement of power. So you take the voltage, you take the current, you multiply them, you get the power. Then the signal proportional to the power is transformed into a frequency, and then simply you count. Use a counter, we have already studied the counter, to measure the pulses. And these pulses are proportional to the energy, because it's integral of the frequency in time, okay? Fine. Okay. Let's talk now about the measurement of RMS value. And as I told you before, let me erase. So far, if there is any question, please type it, and I can answer before we move to the RMS value part of the lecture. No questions? Beep. So, as I explained to you, let's repeat, the RMS value is, RMS stands for root mean square. Okay? So if you don't remember how to calculate it, follow the definition. First, you square. So you take the voltage in time, and you square it. Then you apply the mean. It means that you integrate it over a period 0 from t, and you divide by the period. So this is the mean of the square. And then you apply the square root, okay? Why we need to measure this? Because as we saw yesterday, for instance, if you want to measure the power, which is the energy over the time absorbed by a load, you have to multiply the voltage times the current times the cosine of the angle between them, and these values of the voltage of the current are the RMS values of the current and the voltage, okay? So you want to measure these RMS values because they are connected with the power, therefore with the energy. And in the word, energy, everything is moved by energy. So you are always interested in the energy, because that's what makes the work you want to do. And so, as I explained already before, if you take a sine and you multiply times itself, what you get is twice the difference. So in this case we have 50 Hertz. If you square it, you get 100 Hertz and 0. So the difference of 50 and 50 Hertz. Now you see probably why we are talking about RMS values in this lecture. It's not only because the RMS value of voltage and current is connected to the energy, but because the problem is basically the same. There are some differences, but at the end of the day, you are still doing the same thing. You are multiplying two values. For the power, it was the current and the voltage, and for the voltage, for the RMS value of a voltage, you multiply again two signals. In this case, in fact, you multiply the same signal times itself. The square is just a multiplication of the same signal. There are other methods, however, that you can use to calculate the RMS value. The first one is a rectifier. I've already explained this topic, but let's go over it once more. If you have a voltage, which is a sine wave, what you can do is to rectify this voltage. And what you obtain is the rectified mean value. It means that you have your voltage here. Then you apply a rectifier, and the rectifier gives you this. Okay? Then you get the mean of rectified voltage, and that is not the RMS value, right? Because the RMS is based on the square, not on the absolute value of the voltage. The square of a sine is something like that, which is different. You see, there's this whole difference between these two signals. But we know how much is this difference. If you calculate the rectified mean value and the RMS value following these formulas, so you have to calculate the average of the absolute value of V, of the voltage in the period, to get the rectified mean value, okay? Rectifying means that what is negative becomes positive. Therefore, it's like if you rectify, if you take the absolute value of the voltage. So in this case, simply you have to integrate, if you want to do it at home as useful exercise, you integrate the sine over half a period, and once you have this integral, you multiply times 2 over t, okay, because you have only half a period. So the rectified mean values is 2 over pi, okay, times the maximum voltage. Then the RMS value, you have to integrate the voltage squared, and then take the square root of that, and you get, as you probably remember, the maximum value divided by the square root of 2, okay? Now, if you want the RMS value, what you have to do is to take the rectified mean value and multiply it times 1.11. 1.11 is because, you have pi divided by 2, which is here given by the rectified mean value calculation of the maximum value, and then divided by the square root of 2, okay? So the RMS voltage is the maximum value divided by the square root of 2. Instead of the maximum value, you put the rectified mean value times pi half, which comes from this equation. You can recalculate Vmax as pi over half times the rectified mean value. So instead of Vmax, you write pi half times rectified mean value. And once you compute pi half divided by square root of 2, you get 1.11. Okay? So what you do is to what you do is to measure the rectified mean value, but then on the scale, you convert this value to RMS by multiplying times 1.11. This 1.11 number, this 1.11 ratio between the rectified mean value and the RMS value applies only for sine waves, because it comes from these integrals, okay? These integrals give you the value of maximum value divided by square root of 2 to get the RMS, and 2 divided by pi Vmax in order to get the rectified mean value only for sine waves. If you have different waveforms here, you get a different value of the rectified mean value and RMS value, okay? And therefore that equation doesn't hold anymore, don't hold anymore. So we need better ways to measure the RMS value. Again, you can do a multiplication as we did with the power. So you can use the Hall effect sensor, you use the Log Antilog Multiplier. Again, be careful because the logarithm is defined only for positive numbers. So if you want to measure the RMS value of a voltage, which has also a negative number, you must add a DC bias to the voltage in order to have the voltage always positive, okay? Otherwise, you cannot make the logarithm of a positive, of a negative value, okay? Or I think, yeah, the logarithm of a negative is a complex number, something like that. Of course, you can sample the voltage and then you can compute the RMS value numerically. The same thing we discussed yesterday. Once you are able to sample your signal properly, then you can achieve. You have all the information, and then you can achieve the RMS value by computation. A very important topic is the thermal RMS to DC converter. Okay? Why? Because, as I told you, the RMS value is strictly related to the concept of work. The RMS value tells you how much work is done by that signal if you use that signal to power something, okay? So let's use the very basic definition of RMS value. Let's use a signal to create a work. In this case, a thermal work, heat, okay? How does the thermal RMS to DC converter work? We have two different sections. In the first section, on the left-hand side, you have heat generation, okay? In the first step, the switch are in the upper position, and you apply a voltage Vx unknown. You don't know what the RMS value of this voltage is, and you want to measure it. So our unknown is the RMS value of the voltage Vx. You connect it to a circuit which creates heat. Here in the middle, we have a thermal element which creates a heat due to this current. On the other side, you have a section where the heat is measured. You have a sensor of temperature, for instance, a thermocouple, which generates a voltage Vt proportional to the heat, okay? Then you have a balance indicator, which is nothing else than a device telling you when you have two voltages which are the same, and the generator Vp. So what do we do? In the first step, we produce some heat by applying a voltage Vx to the input, which creates a current Ix. And then we obtain a voltage Vt due to this heat. At this stage, we change manually the value of the voltage Vp so that it will be equal to Vt, the voltage produced by the thermocouple, by the sensor of temperature, okay? So, if we give a current, we create some heat, and this heat creates a voltage Vt, then I go there and I change the value of Vp, the DC generator, until Vp and Vt are the same, okay? If they are the same, the balance indicator says, bingo, 0. Therefore, I know that the two voltages, Vt and Vp, are the same, okay? And then we change the position of the switch. I change the position of the switch and I inject another value of current in the heating element. Generally speaking, this current IN has a different RMS value than the current IX. Therefore, it will create a different quantity of heat. Therefore, the voltage created by the sensor of temperature, Vt, will be different. But Vp still has the previous value of the voltage. That voltage that we applied in order to have a balance between Vt and Vp. So now we produce another amount of heat because we have a different current, In. We will therefore get another value of Vt, and we lost the balance because Vp still remembers the previous value of the voltage that we applied to get a balance. Now, we have a balance in the step 1. We change the heat, we produce another voltage with the sensor of temperature, and therefore we lose the balance. What do? We don't change Vp. Vp is still our memory. It reminds how much heat we generated before. So what I do is to change the current In until it produces the same heat we had before. I increase the current, and when I see that I have a gain balance, it means that Vp is equal to Vt again. But this means that the Vt is equal to the same Vt we had before. The thermocouple, if we are back in balance, remember the thermocouple creates the same voltage we had before when we were creating heating by the unknown current. Okay? What does it mean? It means that now, if we have a gain balance between Vt and Vp, we are creating the same heat, right? We are creating the same heat, and therefore In is creating the same amount of work of the current Ix before. I will repeat this procedure. I have Ix creates some heat, and the heat generates a voltage Vt with the sensor of temperature. I want to memorize this value of Vt created by the sensor of temperature. Therefore, I change Vp until it's equal to Vt. And I know that they are the same when the balance indicator says 0. Okay? So, in this first step, I memorize on the generator Vp the value of the voltage Vt, which is the result of the heat produced by Ix, our unknown resistance. Then I switch the position of our switch, I inject In, and I change In until it produces the same heat. And I know that it will produce the same heat when the balance indicator says 0, because in that case, the voltage produced by the sensor of temperature will be the same voltage we memorized on the same voltage it produced before, and that was memorized on the voltage Vp. Okay? What does it mean? It means that you can have a current. Whoops. You can have a current Ix, which is AC, and the current In, which is constant, but they have the same RMS value, okay? It doesn't matter if the heat is produced by an AC current or a DC current. It is still heat, okay? If you produce an amount of heat by an AC current or a DC current, you don't care, okay? So, you have an input current, which is AC, or it can be whatever, not necessarily a sine wave, okay? It could be, I don't know, some crazy shape like this. Okay? I don't care. I don't care about the shape. It's producing some heat. And then who cares what is the shape of the waveform? Once it produces some heat, and it's the same heat produced by IN in the second step, I will produce the same voltage on the thermocouple. And therefore, who cares about the shape? I converted a current with, generally speaking, any type of waveform into a DC current which has the very same RMS value, which means that the value of the IN current is proportional to the RMS value of the current unknown, of the unknown current IX, okay? That's why it is called RMS to DC converter. It takes a waveform of, generally speaking, any type of shape, and at the output I have a DC signal which has the same RMS value of this one, okay? So you convert any type of waveform to a DC waveform, to a DC value, which has the same RMS value, okay? What is the advantage? The advantage is that, first of all, you don't care about the shape. So you don't have to get crazy about, yes, but if it's not a sine wave, then this 1.11 doesn't apply anymore. No. It has the advantage which is based on the very basic principle of RMS value, which is energy, work. So it really measures the RMS value. One little disadvantage is about the bandwidth, because of course this requires time. Of course, you don't manually change yourself the voltage. There is a system which automatically changes VP until you get the balance indicator to set 0, okay? But this requires time. The fact itself that you have to continuously flip between the step 1 and step 2 requires some time, so you have some limitation in the bandwidth. One very important thing is this. Somebody might ask me, okay, but why do you get crazy about making this system with IX, IN, changing the voltage of VP until it gets equal to... Why don't you simply measure heat, right? We say that the RMS value is gives you information about the work produced by the signal. So, okay, just inject your current of unknown RMS value into the heating element and measure VT. VT will tell you how much work was done by the current, right? Huh? So what's the problem with this approach? Can you spot it? Now we have still we have 9 minutes. Wow, it's a lot. So we have time to see if somebody guesses what's the problem of this approach. This is the last slide, I guess. Yes. So now I want some answers from you. Let's see if you are still alive. Okay, first of all, type in the comment box if you are alive, or if you are just preparing your meal instead of listening to the lecture. So this is a good opportunity to see if you're still alive. And after that, tell me why I cannot use this system, okay? Of course, I can use it, but it's not as good as the system I presented you, okay? Let's see. Maybe I should propose some points, give some extra points, and then to give you motivation for that. Okay, somebody says that he's alive but thinking. Okay, I will let you think as long as you want. Well, until the end of the lecture. Another person is alive, perfect. Everybody's alive but still thinking. But thinking why we cannot use this system, okay? Let's see. Meanwhile, I will clean the green board. Let's see if there is any response. I'm not sure if I should give you the answer or give an assignment for that. Maybe I will give an assignment. If any, okay, let's put it like this. If you manage to answer now and you have still 4 minutes for that, you get 4 points, okay? So 4 points if you answer now, or 2 points later. Okay? Okay, somebody say. Okay, somebody says, maybe the temperature is not easy to measure precisely because temperature needs time to rise to constant value or something like that. You're getting close to the solution. But no, the reason is not that the temperature needs time to rise, because as a matter of fact, you still measure the value of the temperature. Like, he says, okay, I apply my current Ix in this time, and the heating element takes some time to go down here, okay, to the temperature, and then to generate a voltage Vt, okay? Once you arrive there, you get the value. You need to arrive there. That is a problem of arriving later, of bandwidth. As I mentioned, it takes some time to warm up. Therefore, and if then the current changes, it will to another value. It will need time to go to another value. Therefore, you cannot measure variation too fast, okay? Because it doesn't have time to adjust so fast the temperatures. There is some inertia in the system, so you cannot go faster than the value allowed by the inertia of the system. So the problem here, yes, is measuring the temperature. That is a problem. But why we still measure the temperature, as a matter of fact. We measure the temperature Vt, and we memorize it in the voltage generator Vp. And then we want the same value in the second step. So we do measure the voltage of the thermocouple. So Ix does not hit that specific place by the entire circuit. That's the same problem. He says, again, it's true. Ix will create a heat which is released to the environment somehow. Then you can make you can try to confine it, you can try to isolate it in a specific place. fine. But again, you have to tell me the difference between measuring directly the heat and taking the value of Vt and measuring Vt, memorizing in Vp, and then measuring In in the second step. You still measure Vt. Yes, you have leakage of heat, whatever. But you have it in both situations. Both if you measure directly Vt, and both if you use the system. Okay? Because in the system that I proposed to you, as a matter of fact, you measure Vt, and you want, in the first step and in the second step, Vt to be the same. Okay? So you want these two currents to generate the same Vt. So as a matter of fact, you are measuring Vt. But what's the difference of measuring directly the value of Vt? Somebody says the change of temperature is not enough to measure it. It is easier to measure a voltage that we input a temperature. Oh, wow. Let me read it again. The change of temperature. No, wait. We are not. Okay, let me read it. The change of temperature is not enough. No, it's not a matter of change of temperature. It's not a matter of how precise, how much change of temperature, if you can measure big or small changes of temperature. We are in the same temperature range and the same temperature position. I will try to give you a hint. Try to draw a graph with the amount of heat that you produce by injecting a current in a heating element, in a resistive heating element, okay? You have a resistor dissipates some power, and try to draw the power released by a resistor as a function of the current of that resistor, okay? And then you will notice something, and then you will realize that, okay, you will arrive to the solution. Okay, I think it's everything for today. So I said, the first one, this is, of course, this applies only for the first one, okay? For the first student who arrives and tells me, what's the big fuss about this system? Why we use this and we don't measure directly the voltage on the thermocouple? I will give you 2 points. Okay, so have a nice weekend, and please be safe, because now we have a lot of cases of coronavirus in Prague, so please follow the direction of the government and spend your weekend at home studying for this course, of course. Have a nice weekend. Bye-bye.